So for this transfer function, first you need to know what is linear time invariant system. So linear time invariant system. So linear time invariant system, LTI. Okay, linear time invariant system. So for that, see, if you consider any physical problem that is governed by some equation which is known as governing equation, in our consideration we are only discussing the cases where we have the differential equation. Okay, so for example, suppose one linear time invariant system, it is defined by this equation. Suppose an x nth derivative with respect to t, obviously. So let me write it in a more formal way. So an dn x dtn plus an minus 1 dn minus 1 x dtn minus 1 plus so on a0 x, that is equal with bm dmu dtm plus bm minus 1 dm minus 1 u dtm minus 1 plus so on up to b0 u. Now see, this is one LTI system. Okay, where you can see this is a linear equation. See these coefficients, that is ai and bi, these are all constant terms. Okay, and here in this left hand part, basically you are having x xt system, and here in the right hand side what you have ut system. Okay, ut system. So this is linear time invariant system. Here if you have this type of scenario with initial conditions as zero initial condition, then you have a linear time invariant system. So basically at initial point, that means at t equals to 0, all the values concerning with x and u and their respective derivatives all are 0. So in that case you have the LTI system. Okay, so if you have this structure for a LTI, then if you are applying Laplace to both sides of this equation, then after applying Laplace transform in both sides of this equation and with zero initial condition, this equation, you can see this equation, it reduces to the form that is a n sn plus a n minus 1 sn minus 1 plus up to a0 xs is equal with bm s power m plus bm minus 1 s power m minus 1 up to so on b0 us. Okay, so what is this xs and us? Xs and us, they are nothing but the linear Laplace transform of the main function, that is x and u. Okay, here you can think of a system. See this one, see the input and the output. Okay, one example you can take, see here input it is us and the output you are getting as xs, and the system, here you have the system which is here you have the system. So for input that is ut and for output you are getting xt, and the impulse for this system, suppose that impulse it is g of t. Okay, impulse it is this one. Okay, and corresponding to ut, the Laplace transform is us, and corresponding to xt, the Laplace transform is xs, and corresponding to gt, the Laplace transform, say it is gs. Okay, now see what you have, this xs by us, this is nothing but bm s power m plus bm minus 1 s power m minus 1 plus up to b0 divided by an s power n plus an minus 1 s power n minus 1 and so on up to a0. Okay, this ratio, that is xs divided by us, this ratio we call it as gs. Okay, how we are getting, actually see, it has this understanding, see, this xt, this is the output. Okay, xt, this is the output, and this is nothing but the ut convolution with gt. Okay, this is the output xt, and this is nothing but the input, it is getting convoluted with gt. Okay, gt is nothing but the impulse for the system. So if you apply the convolution theorem property, that means the Laplace of this xt, that is xs, which is nothing but us, and convolution, these get multiplied with g of s. So g of s will be here, so g of s. So from here basically you are getting, see, gs is nothing but xs by us. So this setup already we got from convolution property. Okay, so gs, it is given by xs by us, that's what we got here. Okay, now see, gs, it is nothing but the Laplace of our gt function. Okay, so if we want this impulse function back, okay, what is the system impulse? So immediately we have gt as Laplace inverse of this gs. Okay, and that is nothing but Laplace inverse of this xs by us. So this is system impulse. Okay, this is system impulse, and this is how we can get the value. Now this gs, it is known as transfer function. This is known as transfer function. This gs, it is known as, gs is called as transfer function of the given system. Okay, transfer function. So if we are asking the question that find out the transfer function for the given LTI, so immediately what we will do, you will find this ratio, and immediately you will get the transfer function. If the question is find impulse, okay, find impulse for the given system, so immediately you will take Laplace inverse of this transfer function and you will get the answer. So one physical application we will see in the next slide. See, suppose this is the car, and it is going like this. Suppose this is the surface, and here see what you are getting, this is the input, it is, this is the input, and here some impulse is there for the system. Okay, some impulse, that is gt. Okay, and input, what we consider as, suppose ut is the input, and the output, here you have xt. Okay, so in such cases exactly the same notion we can follow, and we can find the impulse function. This gt can be obtained. Okay, gt How we'll get that? This is nothing but L inverse of GS. So L inverse of that XS by US. Okay, so here this is one physical application where, see, this is the input and this is the output you are getting, and by the time, see, GT is the impulse for the given system. Now we are having this idea. Now let's take one question where another basic understanding you should have. See, when I am writing GS is equals to this one, now this numerator and denominator part, that means this part and this part, will determine some specific characters for this transfer function. Okay, so if here in the note you can write down this, here let GS, it is PS by QS. Then here QS, if you set QS equals to 0, this equation, if you set this one, this is known as characteristic equation for the system, okay, and if you solve this, then you will be getting the values of S, which are known as poles. Okay, poles. And if you set PS equals to 0, then if you solve this one and you will get some S value, these are known as zeros of the given system. Okay, zeros of the given system. Now see, pole and 0 we can get. Another thing you should keep in mind, that this S, it is nothing but a complex number. So S has two parts, that is S is equals to real part of S plus, because it is in the S plane, okay, so I times imaginary part of S. So in the S means it stands for the frequency, so we are applying J here, meaning remains same, but instead of I we are applying J. Okay, so S is this one. So now we can take one question and we'll see the situation. Now first take this problem. The response xt of a system to a forcing function ut is determined by the differential equation 9 d2x dt2 plus 12 dx dt plus 13x is equals to 2 du dt plus 3u. So the first part is determine the transfer function, that is they are asking about GS. Okay, second part, find zeros and poles of the transfer function and plot them in S plane. Okay, so these are the two questions we are having. See, first, see, linear invariant system. This is given as linear invariant system. In the question itself it is mentioned that response you are getting xt, and for the forcing function ut. Okay, this is the linear invariant system. So for linear invariant system, you should see first observation should be there as whether this equation is linear or not. See, obviously this is linear, because no such term like non-linearity, for example square or cube or some product terms of this x with their derivative or this u with their derivatives, these are present. These are actually missing terms. Okay, means this term ut square suppose, or ut u dash t, okay, or xt x dash t, these terms are not here, these are missing. Okay, so that's why it is linear. Obviously linearity condition satisfied all the coefficients. See 9, 12, 13, and here also 2, 3, these are present. These are nothing but the constant coefficient. Okay, and also another thing you can observe here, this is because of the linearity. Okay, and time invariant, see here no such term like xt is equals to, suppose here you have u dash t, it is present, it is present. Okay, but here suppose minus t is present, so in that case it is not time invariant, it is not time invariant case. Okay, suppose if you have xt is equals to, suppose x dash 2t, this is not time invariant because scaling it is present, so this type of scaling factor should not be there. Here you have t, simple t, here you should have t. Okay, so this scaling, these things, if it is present, then obviously the system, it is not linear time invariant system. Okay, so obviously this given thing, it is linear time invariant system. Now if you are applying Laplace with the initial condition, obviously initial condition should be 0, initial condition should be 0, initial condition 0, initial condition means at time t equals to 0, all the values for input and output, these are 0. That means basically the system in a stable condition. Okay, now initially all the values are 0. Now if you are applying Laplace both side with the initial condition 0, so what you have, see 9 s square plus 12 s plus 13, here you have xs, here you have 2s plus 3, here you have us. Okay, it is understood that xs means the Laplace of x and us, it is Laplace of u. So now from here gs, it is given by this xs by us. If you write this, so immediately you are going to get this 2s plus 3 by 9s square plus 12s plus 13. This is the required transfer function, this is the required transfer function. Okay, now the characteristic equation, it is given by this lower term 9s square plus 12s plus 13 equals to 0. Make it equal with 0 and now solve this one. So what you are going to get, s is equals to, if you do the calculation, you will be getting minus 2 plus minus 3j by 3. So j means here the same meaning, like I is equals to square root of minus 1, here j is also the same thing, but because you are dealing with s plane, that's why we are writing j. Now minus 2 by 3 plus minus j. So these values, s equals to these values, these are nothing but poles. Okay, and 0, it is given by 0, zeros are given by 2s plus 3 is equals to 0. Now if you solve, s is equals to minus 3 by 2, this will be 0. Okay, only 1 0 for the given transfer function. Now if you want to plot this one here, so just see this is real part of s, this is imaginary part of s. Now the values, see for pole we are going to use cross, and for 0 we are going to use this circle. Okay, so here minus 3 by 2, so this is 1 2 3, 1 2 3, so minus 3 by 2 means minus 1.5. so here you'll be getting this one. Okay, fine. So this one, and this is the 0, only one 0. Another is minus 2 by 3 plus minus j. So here somehow, here minus 2 by 3, so here somehow you will be getting here this one and this one as the poles. Okay, these are the poles, and this is the only 1 0. Okay, so this is how we can represent the transfer function corresponding pole and 0. Another thing you should know, the order of the system. See this characteristic equation, its order is 2, so the system will have the order 2. Okay, so order of the characteristic equation, it is same as of the order of our transfer function. Okay, so this is the idea. Now for the case of stability, one important result we should know, once we have the transfer function, immediately one can get the characteristic equation. Now from the characteristic equation you can find the pole. You can get s is equals to sigma plus j omega. Okay, sigma plus j omega. So this sigma, it is the real part of s, and omega, it is the imaginary part of s.